Hey calculus folks, this is our guided notes for 3.2a, and you already had an introduction in class where we did one of these problems and kind of got the overall idea on it. So when you have position, velocity, and acceleration, there's a very important relationship between the three, and this is the most important part when you go to do any problems. You need to know this relationship. So the other thing about it is, why are we doing 3.2 after we've done 3.3 and 3.4? And that's because I wanted you guys to have the shortcuts, so when you do these problems, you can use the shortcuts, and it makes all the derivatives easier. So here's the important relationship. If this is your position equation, S of t is what we usually use for it. It's different in different classes. Physics sometimes uses x, sometimes uses, I don't know, d for distance, h for height. Sometimes we use s. So anyway, your position, that's like measured in meters or feet or something like that, right? A distance. This is your original graph. I don't know why I wrote this on this side. This is your position. Okay. Now this one is your velocity. How are they related? Well, velocity is a rate of change of your position, and we have an equation for a rate of change. We have a way to get rate of change, instantaneous rate of change, and that's by taking the derivative of your distance. So you have to know that if you have your position function and you take its derivative, you have just found the velocity function. And if you take the derivative of that, you get your acceleration. So because the rate of change of your rate of change is acceleration. It's how fast your velocity is changing. So that would be, either you could do s double prime, which just means take the derivative of the derivative, or you can just take the derivative of your velocity function if you already have it. So this is a super important relationship, that you take the derivative here, and then you take the derivative here again to go from position to velocity to acceleration. Now this is a general equation for falling objects. Any of you in physics have an equation that's pretty similar to this, except you probably don't use -16, because in physics, in the science community, they correctly use meters, which you would use -4.9, which turns into -9.8 meters per second squared. But we use -16 because in feet per second, that's our constant. So why is there always a -16t squared? This is because of gravity. This is the effect that gravity has on a falling object. Now, what is this right here? V with a little subscript 0 means your initial or starting velocity. Now, that could be positive if you're throwing something up. It could be negative if you're throwing something downward. Or it could be 0 if you just drop something. Remember, if you're dropping, you're not adding velocity to it to start. And then if you see an h sub 0, that means your initial height. And usually on this equation, if we're talking height, I actually use h of t, not s of t. So if you aren't dropping something, you're talking about like an automobile going sideways, then you wouldn't use this formula. But anything that's falling in the air, or a projectile being shot in the air, needs this equation. So let's try to use this equation and see how it goes. All right, so you have a kitten named Chairman Meow, which is an awesome cat name. And you have some doubts as to its ability to land on its feet. So, they always say cats land on their feet. So you go to the top of an 80-foot building for a little science experiment. Now, you would never do this, but there's Chairman Meow, and this person's dropping him upside down. We're going to make like a nice cushion. Ooh, a little cushion to land on. You want to see if he turns around by the time he gets to 80 feet and lands on this fluffy pillow. I love my cats. I would never hurt them. But Chairman Meow is an awesome name. My wife vetoed that name for our cats, so I got to put in a word problem. All right. So, a couple questions here. One is an old question. It's find the average velocity from time equals 1 second to time equals 2 seconds. Okay. The second one is find the instantaneous. That should lead you to say derivative velocity for time equals 1 and 2. So we're going to do a similar thing. One is the old school way of finding average slope. This one's going to be looking at instantaneous slope. And how long will it take for the kitten to land? And what is the velocity on impact of this cushioning pillow? All right, so if we're going to do that, the super important thing is we create this equation based off of that formula. So how do I create the equation? Well, it has a negative 16t squared, that's because of gravity, plus your initial velocity, which in this problem, you're just going to drop the kitten. So that means your initial velocity is 0. You're not throwing the kitten. That would be cruel. All right, so you're going to have 0 times t. And then plus your starting height. Your starting height is 80 feet. So a better way to write that, you don't need to write the 0t because 0 times anything. So we're going to answer these questions one at a time on this next page. So the first question for part A, actually before part A, the most important thing you can do before you even start these is write down your 3 equations. Negative 16t squared plus 80, that's what we just came up with. Your velocity equation would be the derivative of that. So negative 32t, the 80 goes away because it's a constant. And your acceleration of over time is just negative 32. And if you look that up, that's how many feet per second. We should probably write that. This is in feet. This is in feet per second. And this is in feet per second squared, or feet per second per second. So negative 32 is the pull of gravity in feet per second squared. We're going to use these in all the parts of the problems. Okay, so let's try it. The first problem is average velocity. So this is an old question. To find an average, we basically need a slope. We need y2 minus y1 over x2 minus x1. So if I'm going to do that, I need 2 points. Okay, and they already gave me the x parts of the points, because our point is going to have a time and a height. So they already gave us time 1 second. We got to find the height for it. And they want to know what time at 2 seconds is. This is basically someone with a stopwatch starts it and they say, okay, what height are they at 1 second into the fall? What height is the cat at 2 seconds in the fall? And you can take total distance divided by total time and get the average velocity. Okay, so how am I going to find that? Well, I have an equation for height. Oh, I should have written h or t. I have an equation for height. I'm going to get it by plugging my time in here. So at 1 second, it's really asking h of 1. So negative 16 times 1 squared, oops, not t squared, plus 80, okay, is going to result in 80 minus 16. So what's that? 64. Okay. And then I'm going to do it again for 2 seconds in. At 2 seconds in, I can tell how high the cat is above the ground by plugging this in, negative 16 times 2 squared plus 80. So let's see what that is. Negative 16, I could probably do this faster, but let's just do it. Times 4 plus 80, it's going to be 16. Yeah, 16 feet. So at 1 second in, so you started at 80 feet, you drop the cat. At 1 second in, he's 64 feet above the ground. At 2 seconds in, he's only 16 feet above the ground. Hopefully flipped over by now. He's going meow. And your average speed, average velocity, is going to be y2 minus y1 over x2 minus x1. So 16 minus 64 is negative 48 feet per 1 second, or negative 48 feet per second. So that's the average velocity. Now, for an easier question, that was a lot more work. So that'd be basically taking the total distance he fell and dividing it by the total time. Part B is easier because it says what's its instantaneous velocity. Well, for instantaneous velocity, all I really care about is this equation because the derivative finds instantaneous velocity, or velocity at a point. So I can do at 1 second, I just have to do v of 1, and I get negative 32 feet per second. You can write FPS or feet per second. At 2 seconds, so this cat is speeding up as it falls down, which makes sense because it's gaining speed the whole time, getting faster and faster and faster. It's moving at negative 64 feet per second. So you can see it speeding up. When it gets even farther, it's going to be moving even quicker. All right, so part C is how long will it take for the kitten to land? That's a little sneaky question that you got to translate. You got to be like, land. What does land mean? Land means its height above ground equals 0. So that was a sneaky way of asking. You got to decode some of these. You got to find when height equals 0. So when you flip it back over, you're like, which one of these three equations will I use? I'm going to use my height equation. And all I got to do is set it equal to 0. So for part C, I'm going to rewrite the height equation just so I have it here. And I'm going to say lands would be 0 equals negative 16t squared plus 80. And then you solve it, I'll get 6, I'll move the 16t squared to the other side so it becomes positive. Divide by 80 by 16. I get 5, oh, that's nice. And then I square root it. You actually get plus or minus the answer, if you know math. 2.24 seconds. Now I get to throw out the negative because negative 2.24 seconds doesn't make sense. And then that's how long it takes the cat to hit the pillow at the bottom. Right, it goes meow. Poof. All right, what's the velocity on impact? Okay, so we just found when it hits the ground, or hits the pillow. Now we need to find out how fast it was moving at the very end, because you can already see it's speeding up, right? It starts at 0 meters per second when you first drop it. 1 second and it's at 32. 2 seconds and it's at 64 going downward. That's what the negative's for. And the last one is, what's its velocity at impact? So we're going to use the velocity equation, which is negative 32t. And I just plug this answer in down here. So velocity at 2.24 seconds and we get, I'll just use the full answer here, times negative 32. And I get negative 71.55. And that's feet per second. So it's cruising. Actually, I kind of want to look that up. Okay, so I looked it up, and 71 feet per second is almost 50 miles per hour. So yeah, that's pretty fast, but I'm sure it's a very fluffy cushion. All right, so that's part 1. I'll come back with another example because that was dropping something down. We're going to look at a different example of shooting something up next time. All right, talk to you soon.